The ability to handle contradictions makes TRIZ a very powerful tool. When we are trying to solve a problem, we normally come across a contradiction. And a contradiction can be in a variety of forms. Examples of a contradiction can be, this room needs to be very big. Well, when we say we want something to have an attribute like big, there is always a reason that makes it a suitable decision. Right? For example, the room needs to be big so that more equipment can be placed here. But if it is big, there is a contradiction. The contradiction is we need a much more powerful air condition, for example, right? Or there are no more big rooms available, so availability of rooms is a problem. So when we look at a contradictions, and in this class we're going to look at engineering contradictions, and engineering contradictions is represented in such a way that when we look at a statement, we look at what is good and what is bad, right? So when we come across an activity and we realize there's something good happening but also something bad happening, then we know that it is a contradiction. And the beauty of TRIZ as a problem solving method is that it does not sweep a contradiction under the carpet. It makes use of a contradiction as a kind of a trigger, a kind of an impetus to reach out, to discover, to help us to find a better answer, an answer that does not try to compromise, but rather to look at how can we gain the most from a contradiction. And that's really what we're going to look today. There are 3 steps involved in solving problems which are modeled as engineering contradictions. The first step is to formulate the engineering contradictions, and while doing so we will identify 2 parameters, and these 2 parameters will be input to the Altshuler's matrix. We'll take a look at this 39 by 39 matrix which Altshuler came out, and it will help us to identify the inventive principles which are recommended or suggested to solve this specific contradiction. And in selecting the principle, we have actually resolved the contradiction by just referring to a knowledge base. And the knowledge base here comes from the extensive study that Altshuler did in looking at hundreds of thousands of patents. So this tool becomes one of the most important tools that's widely used, mainly because of the richness of the content, and it mainly comes from the study of a large collection of humans' inventions which are stored in the patent collection. So engineering contradictions is an important tool in TRIZ, though it is extremely simplistic in use. It allows us to not evade or avoid contradictions, but to welcome contradictions in such a way that we know once we are able to represent an engineering contradictions, we know that it can be solved. And the solution doesn't tell us exactly the final implementation, but it just gives us a few triggers, and we're going to look at these inventive principles next, which will tell us how the outcome of an engineering contradiction can be used to come up with extremely inventive and innovative solutions. Let us take a real example where, in our lives, we come across speed bumps are used in many places to ensure that car speed could be reduced. I mean, it's especially placed in accident-prone areas where reducing in the speed of cars could help to ensure safety of both pedestrians and also the traffic. When we model such a problem as an engineering contradiction, firstly, we want to say what we want to do as an activity. So here, I will say one good way to reduce accidents is by increasing the height of the speed bump, right? So if height of speed bump is increased, then we look at, is there anything good that happens? Yes, the number of accidents decreases, but well, that's actually a vague parameter. Can we relate it to something that's measurable? Okay, we say, well, speed of ongoing traffic or speed of vehicles decreases, right? Speed decreases, and this is something good because as speed decreases, we find that accidents are reduced, right? So instead of saying speed decreases, I could also have said accidents are reduced. But let's just, for the sake of problem solving, look at speed decreases as the improving parameter, right? So this sign here says that the improving parameter is speed decreases. Now, well, when we do this, is there anything bad that happens? So the next thing to look at is there a disadvantage that happens as a result of increasing the height of the speed bump? And one says yes, and studies have shown that 1/5 of the cars that actually have to travel through speed bumps face some sort of a problem. I mean, the problem could be to shock absorbers. I mean, it could be to various parts of the car. But, well, the impact is normally not fully taken into consideration, but the impact can be quite severe. So, what we will say here is it causes damage to vehicles, right? So, we have seen how an example of an engineering system can be represented. So what we saw here is, first we will describe an event or an activity, and then we look at what is good about it, and then we will look at what is worsening or what is the weakness or what is bad, right? So here we have already modeled the first part of the engineering contradiction. So the improving parameter is parameter number 9, which says speed, right? And the worsening parameter, when we look at the list of 39 parameters, we get parameter number 30. Now, the Oculus matrix gives us 4 recommended principles. And in this case, the principles are 1, 23, 28, and 35. So now we will take a look at the 40 inventive principles to find out what these 4 principles are all about. These 4 principles, which are recommended, gives us 4 interesting directions for solving this problem. Firstly, we see here segmentation, which says divide an object into smaller parts. This gives us a clue that we could partition the entire bump into smaller parts such that the harm on the vehicle is reduced. At the same time, we can look at another principle here, which says provide information to enhance an operation, which is principle number 23, or feedback. This means that while the car travels on the part of the road which is aimed at slowing down the vehicle, the car receives some feedback that informs the driver of information that he is going on the right speed. And this may sound like, wow, can this happen? Well, in some countries, there are roads that if you drive at a particular speed, music will come up. Principle 23 suggests that the bump itself could be an optical illusion instead of being a real three-dimensional object. And the last one here, parameter change. Well, I recently came across an interesting idea where a non-Newtonian fluid was used as material to make the bump. And the uniqueness of this material is that when the car travels at a very high speed, the fluid itself becomes hard, and in a way it gives a feeling, inconvenient feeling to the driver. On the other hand, if the driver drives slower, then the Newtonian fluid does not react on the tires and the driver has a comfortable feeling. Well, the problem that we looked at today could have been modeled slightly differently if we were to look at another improving parameter. Instead of speed decreases, we could have said productivity increases. And then the improving parameter chosen would have been 39 instead of 9. And in this case, when we have 39 versus 30, we would have had another 3 different inventive principles which are suggested. Right? So in this case, there's one principle which says the other way around. So this gives us a kind of direction where we can say, instead of the speed bump stopping the driver or reducing the driver's speed, we can say the driver does it himself. Right? So the driver has some form of incentive or some sort of value where when he reduces his speed, he gains some benefit. At the same time, when we look at use harmful factors to get a positive outcome, which is principle number 22, or blessing in disguise, this principle is interesting. I mean, it says that something bad could be turned into something good. Now, if we imagine that people are afraid of broken roads, roads that are, well, under repair, right? So in Canada, they've actually used this idea to reduce the speed of cars. Engineering Contradictions has proven to be a simple tool by just making use of the formulation of problems which are represented as a contradiction. And then by using the TRIS tools, we are able to find clues to very interesting ideas. And these ideas, unfortunately, have already been invented, right? But if you lived in 1930 and came up with Altshuler's matrix, you would have been an inventor with multiple patents.